these are a few problems with the integrated rate laws. Whenever you see first or second or zeroth order, I think you should just automatically write the equation down. So first order reaction has a rate constant of this. Calculate the time required for the reaction to be 75% complete. So we know that the equation is this, equals negative KT, it should be ln actually, plus ln of A0. So because it doesn't give us a specific initial molarity, it just says calculate the time required for the reaction to be 75% complete. I'm going to assume the initial molarity is just 1 molar. So 75% complete will leave me with 0.25 molar. Because remember, A is the concentration of the reactant. So the reactant's going to get decreased by 75%. So when I plug these two in, I can just plug in 1 molar for A0, 0.25 in here, and it gave us a rate constant, plug that in for K, and then we could just solve for T. So when I put that in my calculator, I get 0.25. About 462 seconds. Remember, I said seconds because the rate constant is 1 over seconds. The rate constant could have been like 1 over hours. That means instead of 462 seconds, it would have been 462 hours. Here's a very similar idea. The rate constant for second order is this at 300 degrees Celsius. How long in seconds would it take for the concentration of NO2 to decrease from this to this? So we're literally just gonna, we know this is our equation, A of T equals KT plus 1 over A naught. So it gives us our initial at 0.62, plug that in here, and we know we want it to decrease to 0.28, we'll plug that in here, and it gives us our rate constant, and you plug that in here. So plugging that into my calculator, I get 1 over about 3.63. And again, the unit has seconds, so I know this is 3.63 seconds. Finally, this one says the second order blank is 50% complete after this many hours when the initial concentration is this. How long will it take for it to be 75% complete? So 50% complete is the half-life. So it says the half-life is 5.82 hours. So 5.82 equals the half-life. Well, the half-life for a second order reaction, as we showed earlier, is 1 over AK. So, and it gives us the initial concentration. So when I plug that in, I can solve for K. So solving for K, I'm going to get 5.82 times I get K is about 0.039. So now with K, it says how long will it take to be 75% complete? I could just now plug it into my normal integrated rate law expression. So for it to be 75% complete, 25% of this, 0.25 times 4.46, it's about 1.115 equals KT. I now have K. Plug that in for K, plus 1 over our initial, which is 4.46, and we could solve for T. So I'll solve for T real quick, and I get, and you should never get a negative time. So if you do get a negative time, that's probably a sign that you messed something up. I get here 17.2. Notice how now it's in hours. This K unit was in hours, so now this is 17.2 hours. So yeah, that's some applications, and thank you for watching the integrated rate laws video for today. So another type of problem that looks a little bit different from the ones we did above is they'll give a chemical reaction like this. I just wrote generically A plus 2B yields 3C. Gives you the order, K, the initial molarity, and then asks for the molarity of one of the products after 30 seconds. So let me change this real quick. So it looks a bit different, but you still write out the second order equation or whatever order it gave you. And we see that we have the initial molarity, so we can plug that into here. And we have K, and we also have T 30 seconds. So the first thing we do is we solve for our A at T. So plugging this into my calculator, I get 1/2 plus 0.03 30. And then, so I get the concentration of A at this point is about 0.71. So some students will make the mistake and submit this as their answer, but remember, the concentration of A is the concentration of the reactant, and it's asking for the concentration of the product. So the way we do this is we see how much of A was consumed. So A started with 2 molarity, and now it's at 0.71. So 2 minus 0.71 gives us about 1.29. So that's how much molarity of A was used up. Now remember, for every, as shown in this balanced reaction, for every 1 mole of A that reacts, 3 C's are formed. So 1.29 molarity of A reacted, that means we have to multiply this by 3 to get how much of C was formed. So multiplying that by 3, 1.29 times 3, I get 3.87. So that means the answer to this problem is the molarity of C is 3.87 with this given info, that's second order, and K, and that's 2 molarity initial. So that's the other type problem. These are all the main types of problem. You just flip-flop between the formulas, half-lives, always write down the relevant half-life or rate law, and then you'll realize all the stuff that you have and what to solve for. Thank you for watching. That was kinetics for today.